Swayam Prabha. Digital India. Educated India.
Hello and welcome to Lecture 11 on Special Relativity. In today's class, we're going to see the stunning implications of relativity for how energy and momentum transform from one reference frame to another. We'll also talk about how electromagnetic fields transform from one reference frame to another, and ultimately how Newton's laws are incompatible with the laws of special relativity and have to be modified, whereas Maxwell's equations are seen to be compatible with the laws of special relativity. So here's the plan for today. We'll start by talking about how the mass of particles and the charge of particles can be thought of as four scalars. That is, these are absolute quantities which all inertial observers agree upon, as in the same way that they agree upon the lengths of space-time intervals. Then we'll rederive the four-velocity transformation law in a more interesting way, which seems a lot more natural. Once we do this, we will understand how to modify Newton's laws to make it consistent with Lorentz transformations. Then we will see that just as in Newton's laws, which are compatible with Galilean relativity, we have a concept of energy and momentum conservation. We now have a more generalized version of energy momentum conservation in the absence of external forces in special relativity as well. However, one of the stunning implications that we'll see is that even particles which do not have kinetic energy in a particular reference frame still can have an associated rest mass energy. Okay. So this leads to the famous equation, probably the most famous equation in physics, E is equal to mc square, which just tells us that mass is a form of energy. So we'll discuss some implications of this result when we get to this section. And finally, we'll talk about Maxwell's equations, and we will show how they are compatible with Lorentz transformation. So the first thing we'll discuss is how mass and charge can be thought of as four scalars. So as we've seen, in the rest frame of a clock, the time that elapses on this clock, on an inertial clock, can be thought of as what is called proper time. And this proper time is a Lorentz invariant quantity. That is, every single observer will agree on the value of proper time. They may have different ways of calculating it, but they will always agree on the value of proper time. So if we draw, for example, the space-time diagram of this clock is sitting at x is equal to 0, and in its own rest frame, some time tau ticks on this clock. In a different reference frame, both these space-time points would have different coordinates, but the space-time interval between these 2 points would still be the same, and or every observer would get the same value of that space-time interval, and therefore they would infer the same value of proper time. Similarly, we've seen that if we have a rod which is placed, which is at rest in a particular reference frame, and it has a length L in this rest frame, different observers would measure different lengths for this rod. However, they would agree on what is called the proper length of the rod, or the length of the rod in its rest frame. And the way they would do that is they would measure the coordinates of these space-time points, which appear to be simultaneous in the rest frame of the rod, and they would calculate the space-time interval between those 2 points, and that would allow them to infer the proper length. So they would calculate the proper length in a different way than an observer in the rest frame of the rod, but they would all agree on what the proper length is and what the proper time is. So now similarly, we postulate now, that is, we cannot derive this, but we assume this to be true, that mass, or what is called rest mass of a particle, is a Lorentz invariant quantity, and charge of a particle in its rest frame is a Lorentz invariant quantity. Okay, these seem like very natural things to assume, that every observer, every inertial observer, would agree on what the mass of a particle is, and every inertial observer would agree on what the charge of a particle is in its rest frame. They would have different ways of measuring this rest mass and rest charge, but all observers should agree on the value of this rest mass and rest charge of a particle. Okay, this is our postulate. So let's denote the rest mass of a particle as m, or m naught, and the charge as E or E naught. Okay, so we might switch notations and just write the mass as m and the charge as E. What we mean by this is, of course, the rest mass of the particle, or the mass in its rest frame and the charge in its rest frame. This is the only thing which we assume to be Lorentz invariant. Now, the next thing we'll do is rederive the four-velocity transformation law. Now, previously, we talked about how if we have a reference frame S with, let's say, axes x and y, and we have a different reference frame S prime, which is moving with respect to the reference frame S, and suppose we have a particle which we observe in both reference frames, and in reference frame S, this particle has a velocity with magnitude u and components ux and, let's say, uy. So ux is parallel to the direction of relative motion between S and S prime, and uy is perpendicular to the direction of relative motion between S and S prime. Now, we saw that there's a complicated rule for how observer S prime would describe the velocities of the velocity of the same particle, that is, how they would describe, let's say, u prime x and u prime y. However, when we rearranged velocities in a particular combination, that is, if we took the combinations c over square root of 1 minus u squared by c squared, ux over square root of 1 minus u squared by c squared, uy over square root of 1 minus u squared by c squared, and uz over the square root of 1 minus u squared by c squared, we saw that this collection of four objects transforms like a four vector. That is, it can be related to the corresponding quantities in frame S prime by a Lorentz transformation matrix lambda, which depends on the speed v, okay, or beta, which is v by c. Now, the way we constructed this was rather ad hoc. We sort of guessed that these are the quantities that we have to arrange. But is there a natural way which would guide us towards this guess? Okay, and that's what we're going to look at next. So the way we start is by thinking about the displacement of a particle rather than its velocity. So suppose in a frame S, it's at location x alpha. So this is its space-time point. And now I denote it as a four vector with index notation. So x0 would give me ct, x1 would give me its x coordinate, x2 would give me its y coordinate, and x3 would give me its z coordinate at time t. And let's denote its new spacetime position as x alpha plus dx alpha. So dx alpha is the displacement in its spacetime coordinate. So that is a time dt later. We want to know what is the change in time at which we're measuring its new coordinate, the change in its spatial position, and the change in its dx, dy, and dz. Its change in its x, y, and z coordinates. And one thing should be obvious is that dx alpha is the difference in the space-time 4 vectors of its new space-time coordinate and its old space-time coordinate. So dx alpha transforms like a 4 vector. Okay, so suppose I denoted this as x alpha and y alpha. Both are 4 vectors, and therefore y alpha minus x alpha is also a 4 vector, and that difference is what we're denoting as dx alpha. So this should transform as a 4 vector. Okay, so in general, anything with one free Lorentz index, upper, transforms as a contravariant 4 vector. And now we could also ask, in the rest frame of this particle, okay, in the rest frame of this particle, what is the proper time that elapses? Okay, so the proper time d tau that elapses between these two spacetime points is a Lorentz invariant quantity. Elapses in the rest frame of the particle. This is a Lorentz invariant quantity, or a 4-scalar. And now if we construct the quantity dx alpha by d tau, dx alpha transforms like a 4 vector, d tau transforms like a 4-scalar, and therefore this entire quantity should transform as a 4 vector. Right? The transformation of d tau is trivial, it doesn't change, and therefore the entire quantity transforms as a 4 vector. So what that means is, if I calculate this in frame S, the corresponding quantity in frame S prime, which would be its displacement 4 vector in the frame S prime divided by d tau, and d tau is the same, it doesn't change. This quantity, I can denote it as d tau prime, but d tau prime is the same as d tau. This quantity would be related to our old quantity. So let's just remove this prime, as dx prime alpha d tau is related just by a Lorentz transformation to the 4 vector in the frame S. Okay, so this is the dictionary for transformation of this quantity, and this entire quantity is what we call a 4 velocity. And we'll see that this 4 velocity is related to the thing we had defined earlier in this sort of ad hoc manner. Okay, so let's work out what this 4 vector is. It's dx alpha d tau, and d tau square is the space-time interval that elapses on a clock which is at rest with this particle in any reference frame, as measured in any reference frame. Okay, so in particular in reference frame S, we can calculate this as c square dx0 square minus dx1 square minus dx2 square minus dx3 square. That is, we calculate the space-time interval between these 2 points. Okay, and that would give us the proper time that has elapsed on this clock. And similarly, in frame S prime, we could calculate this as c square dx0 prime square minus dx1 prime square minus dx2 prime square minus dx3 prime square. Okay. So now let's write out the different components. Let's write down, let's just work out d tau in frame S. Okay, a similar result will hold in frame S prime. So d tau in the frame S would be square root of, it's a positive time that would have elapsed if we look at a time in the future. And so we would have c square dx0 square and now what we can do is we can write this as c dt, where I've identified dx0 as dt, into the square root of 1 minus dx by dt square minus dy by dt square minus dz by dt square. And this is nothing but 1 minus, each of these terms is divided by c square. I pulled out the c square. So this is nothing but 1 minus u square by c square, where ux is dx by dt, that is, it's the speed as measured along the x direction, uy is dy by dt, and uz is dz by dt. Or these are the components of what we traditionally call 3-velocity. And so now the 4-velocity vector u alpha, which is dx alpha by dt, okay, can now be written. So if we look at the components, u0 is d dt by d tau, which will just be 1 over the square root of 1 minus u square by c square. And similarly, u1 would be dx by d tau, which would be 1 by c into the square root of 1 minus u square by c square. Let me write it this way. So there's a dx here, and d tau contributes a factor of c dt. So I'll write that here. And dx by dt again is ux. Okay, so I get c. Okay, and so this would be ux prime or u1. And similarly, I can write down u2 as uy over c into square root of 1 minus u square by c square, and u3 as uz over c into the square root of 1 minus u square by c square. Okay, so now so I can write down now the components of u alpha as 1 over the square root of 1 minus u square by c square, ux by c over square root of 1 minus u square by c square, uy by c, and uz by c over the square root of 1 minus u square by c square. Actually, if I was a little more careful, the way I define d tau is not exactly like this. I would have put a factor of c here, and actually c square d tau square is defined this way. And so the factor of c would drop out everywhere in the denominators. So over here in the numerator, I would still have factors of c. So I would have a factor of c in the numerator here. And I would not have this factor of c in the denominator here, or here, or here, or here. So doing this a little more carefully now, we have a factor of c here, and we don't have factors of c in these denominators. Okay, so this gives us our 4-velocity 4-vector, and this we can obviously see from its definition as dx alpha d tau that it must transform as a 4-vector. Okay, so if we define the 4-velocity properly as dx alpha d tau, then it obviously transforms as a 4-vector. Okay, similarly, we could calculate d square x alpha d tau square, and this is called the 4-velocity, and similarly this would also transform as a 4-vector, and we call this 4-vector the 4-acceleration. Okay, this also transforms as a 4-vector. And you can relate it to the conventional acceleration, or the 3-acceleration, which would be d square x, dt square, d square y, dt square, and d square z, dt square, that you would measure in a particular reference frame S. But you would also find that this 4-acceleration depends not just on the 3 accelerations, but it also depends on the 3 velocities. Okay, that is, it depends on ux, uy, uz. And this is something to be expected, because when we looked at our transformation laws for 3 accelerations, which were quite complicated, they depended on the components of the 3 velocity vector. Okay, but if you switch over to this 4 acceleration, things become very simple, right? It's much easier to see that this quantity must transform like a 4-vector. So this is d square x d alpha d tau square, or to be more precise, it's du alpha d tau. Since u alpha transforms like a 4-vector, tau is Lorentz invariant, this entire quantity must transform like a 4-vector. Now let's discuss how physical laws should appear, or the form that physical laws should take, in order for them to be compatible with Lorentz transformations. Okay, so what we mean by that is, if you take any physical law and you ask what this looks like as seen by a particular observer or a particular reference in a particular reference frame S, and ask what this looks like in a different reference frame S prime, the form of the physical law to both these observers should appear to be the same. So both observers should see the same form of the physical law, okay, where S and S prime are 2 inertial observers. Okay, if they do not see the same form of the physical law, then what that would mean is that one observer would have a way to tell that they are different from a different observer. Okay, so there would be a way to identify different states of relative motion. So the fact that no inertial observer can tell that they are special means that each inertial observer has to see exactly the same form of the physical laws. So remember that they may measure different things for velocities, accelerations, and so on, but they all have to see exactly the same form of the physical laws, otherwise they will know that they are in a special reference frame. So what do we mean by the same form of the physical laws? What that means is, suppose we have a physical law where we equate one quantity with another. So this is the left-hand side of a physical law, and this is the right-hand side of a physical law. And the physical law tells us that these 2 quantities have to be exactly the same. Okay, so for example, in Newton's law, this is F is equal to ma. In Maxwell's equations, it relates derivatives of the electric and magnetic fields to charge and current densities. Okay, so now the important point is that if I calculate this in some reference frame S, okay, the form of this law should take exactly the same form in a reference frame S prime, where I appropriately transform the left-hand side and right-hand side. So using my dictionary. So my dictionary tells me how to relate the left-hand side of this equation to the left-hand side of the equation in frame S prime. And the right-hand side, I can also figure out using my dictionary how to transform it into the right-hand side in frame S prime. Now, the important point is that the form of the physical law should remain exactly the same. Okay? So, since we've seen that the most general way to describe dictionary objects that transform under special relativity transformations is to use tensors, if the left-hand side of a particular equation is described by a particular tensor quantity, okay, so let's assume that this is, let's say, a rank n tensor, and the right-hand side is a different rank n tensor. So let's call this A mu1 to mu n. The physical law is telling us that this tensor, if I calculate each of its components in frame S, that should be related to this other tensor where I calculate each of these components in frame S. In frame S prime, we know the transformation rule, which will relate this tensor to a new tensor, okay, T prime. And similarly, A will be related to a new tensor. So what we see is, under Lorentz transformations, if the laws take this particular form, where one tensor of rank n is equated to a different tensor of rank n, in the frame S prime, the laws will take the form where the corresponding transformed tensor of rank n is equated to the corresponding transformed tensor of rank n. If this is true, we say that the laws in frame S prime take exactly the same form as the laws in frame S. Okay, it's just the same tensor T is equated to the tensor A. It's just that you have to use a different or transformed tensor T, T prime, and a different transformed tensor A prime. This would not be true if, in a physical law, the left-hand side of the equation was not a fixed tensor. Okay, that is, supposing I had something like U alpha. Okay, and to this, if I take U0, I add U0 plus M. And if I have U1, I add U1 plus E, let's say. Okay, or things like this, where the quantities here transform as components of a 4-vector, but the quantities that I'm adding here are, let's say, 4 scalars. Now, the left-hand side of the equation doesn't have a well-defined transformation law. That is, each part of it has to be transformed separately when I go to frame S prime. Okay. And so now when I do this, what I would find is, if I do not have a well-defined tensor on the left-hand side of the equation, a well-defined tensor of a particular rank, then the law will not take exactly the same form in frame S prime. Okay, and therefore we would have a way to distinguish between these reference frames because the laws do not appear to take the same form. Such a law would be incompatible with the law of the dictionary of special relativity. Okay, so finally we can say that for any physical law, the important thing to be compatible with the dictionary of special relativity is that it should take the form that if I have a tensor of rank n on one side, I should have a tensor of rank n on the other side of this equation. And this is the only way in which this law would be compatible with the dictionary of special relativity. So now that we know the form that physical laws should take in order for them to be compatible with special relativity, we can go back to two sets of laws that we're familiar with, Newton's laws and Maxwell's equations. And we can look for their compatibility with special relativity. Now, as we discussed at the very beginning of these lectures, Newton's laws are going to be incompatible with special relativity because in Newton's framework, time is absolute and the speed of light is not constant to all inertial observers. Okay, that is, Newton's laws obey Galilean relativity rather than special relativity. So if we look at Newton's second law, so Newton's second law tells us that force is mass times acceleration. Now, under rotations, we would easily see that the force would transform to some rotated force vector, and the acceleration would transform to some rotated acceleration vector. So the laws preserve their same form under rotations. Okay. However, under Lorentz transformation, what we would need is what we would need for the law to retain its same form is that the dictionary should tell us that the force transforms to some f prime and the acceleration transforms to some a prime. Let's assume m is the rest mass, so it doesn't transform, in such a way that, that the form of the equation is preserved. But as we've just discussed, the only way to preserve the form of the equation under Lorentz transformations is if the quantity on the left-hand side of the equation and the quantity on the right-hand side of the equation transform as tensors of the same rank. So the first thing is we want is left-hand side and right-hand side should transform as tensors of the same rank under Lorentz transformations. The second thing is, we know Newton's laws are a good approximation, at least for speeds much smaller than the speed of light. Okay, so in the limit where we make a transformation where the speed is much smaller than the speed of light, or the speed of objects that we're looking at is much smaller than the speed of light, then the law should take the form f is ma, okay, in that limit. So this gives us an idea for how we can possibly generalize Newton's laws so that they are compatible with the transformations of special relativity. Okay, and to do that, the simple idea is, instead of looking at three vectors, that is, things that transform under rotations, let's look at four vectors. So what we're looking for now is a generalization of the left-hand side and the right-hand side of Newton's laws. So something of this form. Okay, we need a four-vector f mu, and we want to set this equal to mass times acceleration. Okay, where this is the acceleration four-vector. And this is some generalized force, which is a 4-vector force. Okay, we don't quite know what this 4-vector force is, okay, but we can guess that the form of the law should take some form like this. Okay, so this is a guess for the form of the law. And another important point is, since we want the right-hand side to transform like a 4-vector, this quantity m should be Lorentz invariant. So natural choice for the mass would be the rest mass of a particle. Okay, the particle which is experiencing these forces. Now, let's, so rather than try to study this more complicated law, let's study this law in a particular limit where the external forces are 0. Okay, that is, imagine a system where I have no external forces, or let's just take a single particle on which we have no external forces, and let's ask what Newton's laws imply. Okay, so this generalized Newton's law would imply that the mass times acceleration of such a particle would be 0, mass times 4 acceleration. Okay, so when we say 0, of course what we mean is for each component of the acceleration, the 4 acceleration, it's 0. Now we can recall what the definition of 4 acceleration is. The 4 acceleration is the derivative of the 4 velocity with respect to the proper time of the particle. Okay, which we can write in a slightly different way. We can write it like this. Okay, and this quantity, we can think of it, this is mass times 4 velocity. And this is a natural candidate for what we would call 4 momentum. Okay, so just like we define 3 momentum as mass times 3 velocity, we define 4 momentum as rest mass times 4 velocity. So this is what we call 4 momentum. And what we see is Newton's law, this generalized guess for Newton's laws would tell us that dp mu d tau is 0. Okay, so if we solve this equation, it tells us that the 4 momentum is constant or is conserved. Okay, and the important point is that the form of this law is the same in any reference frame. So I wrote this law down in a reference frame S, but if we were to write this law down in a reference frame S prime, we would simply write down dp prime mu d tau is 0 in the reference frame S prime. Tau is the same no matter which frame you calculate it in, because it's just proper time of the particle. And p mu transforms like a 4 vector. So the law preserves the same form in any reference frames. Okay. And so what this is telling us is that in any reference frame, okay, the 4 momentum p mu is conserved. Okay, so this would be true in frame S, but it would also be true in a different reference frame S prime. So in the absence of forces, for momentum is conserved. Okay, so let's explore this a little more. Let's ask, what is this quantity p mu, and what are these 4 things that are conserved? So p mu is m times u mu, and let's write down explicitly each of these components. So if you recall the components of the 4 velocity, it's mc over the square root of 1 minus u squared by c squared, where the particle has a velocity u in the frame s, and whose components are ux, uy, and uz. So this is what we mean by the momentum 4 vector. Okay, these are the components of the momentum 4 vector. So what Newton's second law is telling us is, in the absence of forces, each of these quantities is conserved in the absence of external forces. Okay, so let's try to understand now what each of these components are. Okay, so and this would be true, remember, in any reference frame, whether you're in a frame S or in a frame S prime, all of these 4 quantities would be conserved. Of course, ux, uy, and uz would change as I go from one reference frame to another. Okay, so now let's look, for example, at the x component of momentum, for momentum. This is mux over square root of 1 minus u squared by c squared. This is conserved. Now, what you see is, in the limit that u is much, much less than c, px is approximately m times ux. Okay, so we recover Newton's laws for standard 3 momentum conservation in the absence of external forces, when the speeds of particles are, so the speed is u, when the speed is much, much less than the speed of light. Okay, so we've got a generalization of Newton's laws which seems to give us the right physical effect in the limit that the speed is much, much less than the speed of light. Okay, and this would similarly be true for py and pz as well. Okay, in the limit u much, much less than z, py would just be m times uy, pz would be m times uz. Okay, now we could ask, well, what about this new thing? Okay, so previously we had 3 vectors, now we have 4 vectors. So what is this quantity over here? Okay, so in other words, what is p0? So p0 is m times c over the square root of 1 minus u squared by c squared. Okay, and it'll actually be useful to think about p0 times c rather than p0 itself. So let's think of p0 times c. This is mc squared over the square root of 1 minus u squared by c squared. Now, this quantity, the claim is that this is conserved, right? The generalized Newton's law would tell us that this is conserved in the absence of external forces. External 4 forces. Okay, 4 vector forces. So now let's ask, well, what is this quantity? Maybe we can gain some intuition, okay, by asking what is this in the limit that u is much, much less than c. So p0c would just be mc squared in that limit. All right. However, we could do better by going to next order in u. Okay, so we would use the binomial expansion of this denominator, and we can write this as 1 plus half u squared by c squared. And at next order, we would have things like plus minus half minus 3 by 2 u to the 4 over c to the 4 by 2 factorial, and so on. So we can now write this as mc squared plus half m times u squared plus 3 by 8 m0 or m u to the 4 over c squared, and so on. Okay, and if you look at this first leading order correction, okay, to P0c just being mc squared, this just looks like your kinetic energy in Newton's theory. And in the absence of external forces, or in the absence of a potential energy, the kinetic energy is the total energy of a particle. Okay, so a natural guess for what this quantity P0c is that this might be the right expression for what we should call energy of the system. So the energy of a particle in the absence of external forces is mc squared plus half mu squared plus 3 by 8 mu to the 4 by c squared plus so on. This is the energy of a particle in the absence of external forces. Okay, so what is kinetic energy? Kinetic energy is just the energy possessed by a particle due to its momentum, or due to its velocity. Okay, so the fact that the particle has a velocity gives rise to some energy. But what we see is that even if the particle's energy was 0, the particle would still have some energy. Okay, so even for a particle of 0 velocity in some reference frame, in frame S, it would have an energy which would be mc squared. Okay, so this is the most famous equation in the history of physics. E is equal to mc squared. Okay, so this is called rest mass energy. And what this equation is really telling us is that mass, or rest mass, the fact that particles just possess mass, is an indication that they have energy. Okay, so normally we could always add any constant to the total energy and not worry about it. Okay, because as long as this energy is locked up inside the particle, it doesn't matter. However, the fact that this, if we look at the exact expression for energy, which is P0 times C, this is m times c squared over the square root of 1 minus u squared by c squared. So it's only in the limit where the speed is much less than c is that where we think of the rest mass energy as being something completely distinct from the kinetic energy of the particle. However, when you look at this expression, you see that the rest mass energy is just a very particular limit of the energy of a particle. It's the energy in when the particle has 0 velocity in a particular reference frame. Now, if there was some way to unlock this energy, okay, that is, you could convert this particle from one form to another, let's say through a radioactive decay or some kind of collision process, then it would be possible to transfer that rest mass energy into other forms of energy. So previously in Newton's laws, we had a separate rule assuming conservation of mass. Okay, this was just an assumed thing, and in the absence of external forces or an external potential, we also had conservation of energy. Now we find in special relativity, the only thing that's conserved is this quantity, P0 times C, in the absence of external forces. And this quantity is what we call energy or mass energy. Okay, it's a combination of mass energy and kinetic energy. And so there's only one rule, okay? So in special relativity, the generalization of Newton's laws tells us that there's only one conserved quantity for mass or energy, and that is a generalized conservation of mass energy. Okay, or sometimes this is just called energy. And in the limit that the speeds are much smaller than the speed of light, there's a separate conservation of mass and a separate conservation of kinetic energy. Okay, and of course we're neglecting corrections which are suppressed relative to the original kinetic energy by order of u squared by c squared. So as long as the speeds are much smaller than the speed of light, these extra corrections are small and we ignore them as we do with Newton's laws. Okay, so we'll explore some implications of the conservation of this mass energy in a moment. But before we do that, let's just ask another question, which is, now that I have this 4-vector p mu, we can construct a Lorentz invariant quantity by constructing the dot product of p mu with itself. Okay, that is, we can construct the quantity p mu, which should be Lorentz invariant. And this quantity, where this is a covariant 4-vector and this is the contravariant 4-vector, or I can write this using the metric g mu nu as g mu nu p nu, or I can write it as, in matrix notation, p transpose dot g dot p. Okay, all of this is 4-vector dot product, and this quantity is going to be equal to, so if you remember p mu now, p mu, we interpreted the components as some generalized energy, okay, some generalized momentum. So these were the components of p mu. And so now what we're going to get for this dot product will be e square by c square minus px square minus py square minus pz square. And if we plug in expressions now for E, which was mc square over the square root of 1 minus u square by c square, and for px, which is mux over the square root of 1 minus u square by c square, and so on for py and pz, then what you would find is that this dot product would just give you m so it would be m times c, okay, which is Lorentz invariant. So the 4-vector dot product of momentum just gives us a Lorentz invariant quantity. And in fact, this is how you would infer the mass of a particle, is in different reference frames, each observer would measure different momenta. And if they calculated, if each observer calculated in their reference frame what this 4-vector dot product is, they would get the same answer. And they interpret the quantity that they get as the mass of the particle times c, or the rest mass of the particle. This is just like how when different observers want to calculate proper time, they would use the distance between two space-time points calculated in their own reference frame, and the result would just be proper time, okay, of a particular clock, where the space-time interval is calculated between two space-time points which are measuring the proper time of this clock in its rest frame. Okay, so you can use the form momentum to actually infer the rest mass of the particle if you're in a reference frame which is not at rest with the particle. And now if we write this out explicitly, okay, so the relation that we found is that E square over C square is E square by C square minus Px square minus Py square minus Pz square is, sorry, I made a mistake here. This is M times C the whole square. Okay, so this is M times C the whole square. So if we simplify this equation, we can write this as E square is vector P square plus P square times C square plus M square C to the 4, where the vector P is the components of this generalized form momentum. So that is, if I take Px, okay, that would be M times Ux over the square root of 1 minus U squared by C square, and so on for Py and Pz. Okay, so these are the components of what we call vector P. And if we and the mod of vector P square is just Px square plus Py square plus Pz square. Okay, so this is our generalized relation between energy, momentum, and mass. Or we can write this as E is equal to square root of mod P. So I'm just going to drop the vector sign, but mod P is the mod of this vector. Mod P square C square plus M square C to the 4. And again, we can expand this for U much less than the speed of light. So for U much less than the speed of light, what that tells us is that P, or any component of P, or mod P, is much, much smaller than mass times C. Okay, so treating this as a very large term and this is a very small term, we can now expand this. So you can show again via the binomial expansion that this is mc square plus, we can write out corrections to this now, plus P square by 2m minus 1/8 P to the 4 by m cube C square, and so on. Okay, so once again we see that their energy is rest mass energy plus conventional kinetic energy of Newton, and you have higher order corrections now.